coming anyway. I'm Mike, WY2U, and I'm here to give a talk today on a project that I initiated about a year ago called Small Loop Antenna Design. There's actually two samples of them here. The breadboard that I did, and Mr. Mike and 2PPI did a similar version that covers similar frequencies with slightly different construction techniques, and I want to talk about both of them, and also would like to talk about how the design evolved. Got to do a little bit of math, but we're going to save the whole thing by putting up a spreadsheet later on and show you how you might be able to build your own using a spreadsheet, and then before you actually build it, be able to predict sort of what the behavior of the antenna is supposed to do. Okay? So here were the goals anyway. The design goals on this project were to design and construct a low-cost multi-band transmitting loop, hopefully of high efficiency, hopefully, and to compare the performance of the antenna to a conventional half-wave dipole or maybe even an isotropic radiator. Would like to see how it fares out. And then I'd like to also hopefully develop a computer spreadsheet that shows that the design was successful and make it easier to hopefully reproduce later on. That was the goal of the project. Now, people have built these things before, but I've read a lot of literature that was kind of contradictory, things I didn't like, things that didn't make sense, and my investigation was to try to either confirm or not confirm some of the things I've read, and maybe at the same time come up with something that can be used for people that need a portable antenna. And that's kind of what I wanted to do with the whole thing. Anyway, here's the design parameters that I wanted to work with. The frequency range wanted to cover at least 14 megahertz to 25, and if I could, try to get 30 megahertz also as a design goal. And turns out I wasn't successful, but we'll go through that in a moment. I'd like to have it remotely tuned. The one Mike did is locally tuned mechanically. This will be tuned with a motor so I can put it up high and tune it from the shack. Both horizontal and vertical mounting. This way you could take advantage of all wave propagation or radiation like a dipole, hopefully. And I want it to handle at least 100 watts so that it's compatible barefoot with a barefoot transceiver. Those were the design goals. And let's keep it light, small size, and I want to keep it cheap. The design goal was to try to keep the cost of materials to be less than $100. Well, let's see how we did, all right? Also, I'd like the pattern and gain of the antenna to be compatible to a half-wave dipole full size with a VSWR of less than 1.5 to 1 on all the design bands at the resonant frequency. All right, so what are we going to choose? We decided, now you have two choices. Actually, you have three choices. You could make a circular loop, a square loop, or a so-called delta loop, a triangular loop. All of them are similar. But to me, the simplest construction was to use a circular loop. This way, the mechanical construction would be as simple as possible. I tried to use, like Mike did, 1-inch copper tubing. This is what, half-inch?
Yeah,
This is plumber's refrigerator tubing. But the darn thing was so heavy and copper is so expensive that I dismissed it and decided I wanted to try something else. So the first cut design that I came up with, the paper design, said in order to cover the frequency ranges I wanted, about a 36-inch diameter loop was about the right choice. And that would be a good compromise between efficiency and frequency coverage, and you can go all through that in the ARRL handbook if you want. They go through pretty much the tutorial. But believe it or not, I have a granddaughter, a child's hula hoop had about the right dimensions. It's about 34.5 inches in diameter, but you got to coat it with material. It's lightweight. The dollar store had it for $1. You can't ask for cheaper than that. So I figured, let's see if we can investigate what it might take to put some kind of a conductor material on the loop itself. 3M makes a product. It's called, I guess the part number is on the next slide. 3/4 inch diameter, copper tape. I have a piece of it over here. At least I did. Oh, it's in the bag. Where's that bag of mine? Hold on. No, the bag is right there, man. I'll pass it around. Yeah, there's a piece of copper tape in there.
Yep.
There you go. Here's a strip. It is sticky on both sides. On one side, that is. And it is copper. And all we have to do is determine whether or not, at the RF frequencies that I want to work at, whether or not it's thick enough so that it'll be lossless. Well, For that, we'll determine the skin depth, and I'll come to that in a moment. For remote tuning, I wanted to use a hobby motor. I have a 3 RPM hobby motor. This is the same kind of motor that you'd find in the motorized boats that you see that move the rudders. Costs about $2. And this motor would actually rotate in both directions. So also, in order to keep the wiring as simple as possible, I decided it would be a good idea to not only put the RF up the coax, but to come up with some kind of a control box that would feed the DC control signal at the same connector as the RF, and this way you can remotely tune it with only one connection. That was the design goal. So we have to design a control box with a reversing switch. So here was the big design unknown, whether or not you can use a conventional tuning capacitor as the tuning element for the loop. I have seen numerous pieces of literature which say you cannot, because they say they're too lossy. Some of what I read didn't make any sense, so that's what prompted the investigation. You've heard of a butterfly capacitor? You know what a butterfly capacitor is? It has one tuning shaft and 2 arms that rotate. And the whole theory about that is the active RF never goes to the shaft, and the shaft is only used as a parasite to couple capacitances between the 2 stators. And they claim the Q of those types of butterfly capacitors is much higher. Also, people have talked about building their own cylindrical capacitors using a stepper motor. Now, the theory there, of course, is you got 2 cylinders with air in between, and the losses there are very low. Yes, it's true, but I needed to find out whether or not this would work, how much better or worse using that approach would work rather than a conventional capacitor. This capacitor here is between 10 and 60 picofarads, $15. This capacitor is between 20 and 250 picofarads if you wanted to go down to a little lower in frequency, and this would be $25. A cheap butterfly is $75. The whole idea was to try to keep the cost down. So that was the approach. Okay, definitions. What is a small loop? It is a completely encircled antenna whose entire circumference is less than a quarter wave. If it's a quarter wave, it's self-resonant. If it's greater than a quarter wave, it's a large loop. What is directivity? In other words, gain. The ratio of loop gain, or directivity, compared to the radiation pattern of an isotropic antenna. It can be expressed as a ratio or in dB. Loop efficiency. The ratio of loop radiation resistance divided by the sum of all the losses in the circuit. Copper loss, capacitor loss. Those are the 2 losses. If you want it as a percent, multiply by 100. Skin depth. Who knows what skin depth is? That's the depth of penetration between the top of a conducting medium to where the RF, or in this particular case, the AC signal falls off to a negligible value. For skin depth, it's defined as epsilon. Epsilon or delta. 1 skin depth is where the RF field drops to 37% of the value on the top. If you go through 2 skin depths, most of the field strength is between 82% of the field strength on the top. The design approach here was to use 2 skin depths. We'll get to that right now. So how do you calculate skin depth? I had to derive this equation. Delta is approximately equal to that number divided by the square root of the frequency, where the frequency is in megahertz. The skin depth comes out in inches. At 14 megahertz, which is the lowest frequency of this antenna, the skin depth is about 1.38 mils. A mil is about 1,000th of an inch. At the top end, if I was going to design it for 30 megahertz, the skin depth would be about 0.47 inches, or 2 delta, 0.94 mils. Well, did we lose our network connection? Something just fell. Okay. Turns out, this particular tape, maybe next slide. The worst case is at 14 megahertz. 1 mil is a 1,000th of an inch. A minimum conductor thickness of 1.38 mils would be required for 2 delta skin depth. 3M, part number, here it is, 1181, has a thickness of 1.4 mils. Just makes it. So it's a good choice for 14 megahertz. It probably wouldn't work very well at lower frequencies, where the skin depth would be maybe double, but maybe you can double up on the tape too, if you're clever. But down to 14 megahertz, 1 tape thickness should work just fine. Okay, now here's the design procedure. A little bit of math. First, you got to choose a diameter of the radiator itself and a diameter of the conductor. Both you want to choose in inches. But you must make sure that capital D, the big diameter of the loop, is less than 3478 divided by pi f, or the loop is not small. At that frequency, it's self-resonant quarter wave. Once you determine the diameter of the loop itself and the diameter of the wire, then you can calculate the loop inductance from this equation right here. We don't have to go through it. I have the spreadsheet that does it later. Next, calculate the inductive reactance based on the inductance that you just calculated. But here you want to do it twice. Sir? It is. Yes. According to Mr. Lanzau, it is. This and the spreadsheet should be there. And now what I'm going to do is immediately after this, I'll go home and I'll put it on my webpage, and I'll give you the webpage URL also, okay? It'll be there someplace. So next you want to calculate the inductive reactance, but you need to do it twice. The lowest frequency and the highest frequency. XL, 2 pi FL, etc., where the inductive reactance comes out in ohms, F is in megahertz. Now, you got to calculate self-capacitance. All of these calculations I'm not going to bore you with. We're going to do them later. You calculate the loop self-capacitance, because now you know, based on its inductance and self-capacitance, where its actual resonant frequency would be, and you better be lower than that, or else the loop is not going to be small anymore. And we'll have to get to that in the spreadsheet in a bit. Calculate the capacitive reactances necessary to resonate the loop. There's a minimum capacitance, which will be the highest frequency, and a maximum capacitance, which is going to be the lowest frequency. Why do you need that? You need to know the tuning range of the tuning capacitor, obviously. Next, estimate. Now here's the interesting thing. You have to either estimate or measure how much losses you expect to get in a tuning capacitor. Well, it turns out I have a Q meter home and a reactance meter. I'm able to measure it. And I found out that the Q of a typical standard capacitor varies between about 2,500 at maximum capacitance and a little more than 1,000 at minimum capacitance. I have a butterfly capacitor home too, which varied a Q of about 4,500 at maximum capacitance and around 1,500 for the split rotor butterfly. Now somebody might say, well, stop right there. The butterfly is the way to go. We'll see. We'll continue. Now, these steps that I just talked about, or the ones that I'm going to be coming up, have to be done twice. Lowest frequency and the highest frequency. Step 7, calculate the loss resistance based on Q. Once you know the Q of the capacitor, you calculate its equivalent resistance. That's a number we need for efficiency. Step 8, calculate the loop radiation resistance. How much loss is there in the copper of the loop itself, plus the matching, which we can do based on copper alone and skin depth. Okay? That's this equation in step 8. Step number 9, calculate the total loss. Capacitor plus antenna. Total loss resistance. Add them together. Step 10, now you calculate what the loop radiation resistance is. And you can get that from physics and Ohm's law and Gauss's law for inductance. This is actually a simple equation. And you can calculate the loop radiation resistance twice. Lowest frequency, highest frequency. Calculate the antenna efficiency, and here's the very important calculation for zeta. Zeta is the Greek letter for efficiency. It's the radiation resistance divided by the sum of total loss plus radiation resistance times 100 if you want it in percent. If you want it as a ratio, don't multiply by 100. We're going to find out that at about 20 megahertz, it's about 25 to 30% efficient. At 24 megahertz, it's about 75% efficient. And we'll see what that means with respect to radiation pattern in a moment. Now calculate the antenna Q. Why do we need Q? How wide of a bandwidth can we operate at before you got to retune the capacitor? Okay, we can calculate the antenna Q based on its inductive reactance that we calculated way up front versus total resistance that we just calculated. Now, an important calculation. What is the voltage across the capacitor? That determines the plate spacing. The voltage across the capacitor is the square root of the power that you're going to run times the inductive reactance times the Q. That comes out in volts. That's peak voltage, because I'm using peak power. Now, what does that mean? How much plate spacing do I need? The plate spacing is approximately equal to 2 times the voltage we just calculated divided by 50,000. That's got a 2 times safety in it. I'm assuming that air, sea level, 25 degrees C, breaks down at 50,000 volts per inch. That's where that calculation comes from. Yellow is important. Make sure, oh, sorry, I jumped ahead. Make sure that you choose a capacitor offering at least the minimum and maximum capacitance values that you calculate with the minimum plate spacing that you just calculated in step 14. Or else what happens? It's going to arc over. Yeah, simple as that. Calculate how much peak resonant current you have in your loop. This is a surprising calculation. What do you think? At 100 watts, how much current do you have here? The spreadsheet will show it later, but what do you think? 10 to 14 amperes. Yes, it gets warm. Calculate your loop bandwidth based on Q. That's step 16. And for that calculation, all these calculations, step 11 through 16, we are assuming that all of the power that we put out from the transmitter is getting to the antenna, obviously. And the only way that's going to happen is if the match is good. If you have a match better than 1.5 to 1, 94% of your energy is going to get to the antenna. So that's the design goal. Make sure these calculations are closed loop and stand alone. That's the reason why you want to try to match it. Okay, so here's a gain estimate for the antenna. When you're all done and you got it designed, your gain in dB as an estimate, 10 times the log 1.64 times zeta D. Zeta D is the efficiency number that you calculated, I think, back in step 8 as a decimal. And this is the gain reference to an isotropic antenna. If you want the gain reference to a dipole, subtract 2.14 dB. Okay? That's all our design calculations. Who wants to do one? No. I did. But I may have an easier way. We have a spreadsheet. And if you let me, the spreadsheet's going to permit a fast design on the personal computer by actually taking all those steps and automating them, obviously, or else why bother? The spreadsheet is going to be now a function of all the loop parameters. You're going to put in a couple of parameters like the size, diameter, etc., frequency, and it's going to recalculate everything you need to make the loop. If you make a mistake, hopefully the spreadsheet should tell you. So it's going to trap any errors that you may have put in there. And we hope that's the case. So now let's go to the spreadsheet. I just got to figure out how to get out of this screen now. Screen, switch programs, and I can't find it. I think this is it. There you go. Okay. This is all the design parameters that I just talked about with respect to a circular loop. You're going to put in your loop diameter, your loop conductor diameter, the frequency, how much power you're putting out, and an estimate of capacitor Q. Well, now you're going to say, well, how do I got that? Well, I did that over here. Let me move this down a little bit. Can I make this smaller? Hold on. I want to try to get this whole thing on one screen if I can. Is that okay, or is it too small? Okay. Here, the capacitor itself, Q versus frequency, based on that design. So now, that design has a 60 picofarad capacitor, which resonates at about 14 megahertz, versus a, let me get up a little higher here, a 15 picofarad capacitor that resonates at about 25 megahertz. All right, so let's go do a design. This particular loop has a design diameter of 34.5 inches. I'm going to try to make a 36-inch loop. I'm going to change the parameters a little bit. The conductor diameter, which is the diameter of the hula hoop itself, happens to be 0.875. I'm going to try to make it 0.75. I'm going to muck with the design a little bit. The frequency will be 14 megahertz. Let's keep that where it's at. The transmit power will be, leave it at 100 watts. And now I have a choice of what the capacitor Q wants to be. Well, I chose, or I'd like to choose, a regular capacitor rather than a butterfly. At 14 megahertz, the blue trace here is a regular capacitor. At 14 megahertz, a butterfly capacitor is the purple, or pink, whatever color that is. So let's put in the Q for a regular capacitor. So if you match it up with the graph, it's about 2,500. Yeah, I'll make it 2,400 just to change the number a little bit. hit the enter button, and everything over here gets recalculated. The loop inductance is 2.27 microhenries. A loop inductive reactance, just under 200 ohms. How much capacitance do I need to resonate? About 57 picofarads. My total loss resistance is 0.134 ohms. Don't sound like much, right? Except the radiation resistance is 0.06 ohms. The loop efficiency is 32%, which means the estimated gain with respect to an isotrope is actually less, minus 2.7 dB, with an antenna Q of 503, a bandwidth of 28 kilohertz. That means that you don't have to retune it. You got to be within 27 kilohertz, plus or minus 13 kilohertz, 14 kilohertz are where you want to be. You want to move further than that, you got to retune. How much added capacitance do I need to resonate the loop? Because the distributed capacitance on its own is 2.5 picofarads. I got to add 54.4 picofarads. There's 3,168 volts across the capacitor at 100 watts. Well, let's say I got brave and I want to run this at a kilowatt. Ha ha. You got 10,000 volts across the capacitor. I wouldn't recommend it. 100 watts looks like it'll be okay. By the way, we'll check it. Back to 100 watts. That says the minimum plate spacing is 0.13 inches. This is just under 0.1/8. That's 125. This is okay. This capacitor will handle it. This probably will not. And there you go. There's a design. You happy with it? Well, maybe not. I want to use a hula hoop, so I want to make it 34.5 inches. Whoops. And it's 0.875. That's my hula hoop dimensions. And my Q is really 2,500. So you can see how quick this thing updates. Boom. All the parameters now are recalculated. I can examine them. There isn't much of a difference. So, you know, I got a 32% efficient design with a little over 3,000 volts across the capacitor and roughly the same plate spacing, so it looks like I'm good to go. Now, say I wanted to spend some money, and I wanted to say, well, how much better would it be if I spent the money and went for the butterfly capacitor? So I matched that up. That has a Q of about 3,500, so I'll change the 2,500 to 3,500. And I went from 32% efficient to 37% efficient. A $15 cap versus a $79 cap. You choose. If it's worth it for 5%, you got it. The gain went from minus 2.7 dB. Oh, wait a minute. Or was it 2.6 dB? I don't remember the number. Yeah, minus 2.7 dB to minus 2.15 dB. The gain went up 0.6 of a dB. That's about the thickness of the needle on your S meter. It is your choice. You know, you want to spend the extra money for a better part. It does work better. I'm not putting the design down. A butterfly cap will give you better performance. But the trade-off may not be so acceptable in terms of what the impact will be on cost. So I chose this approach. All right, so now I said, well, okay, good. That works pretty good on 14. Let me try the same design without changing anything else other than frequency, and I'm going to go to 30 megahertz. 30 megahertz, okay. It looks like it would work. The loop inductive reactance is a little more than 2 microhenries. It's a 389 ohm inductive reactance. The efficiency is 86%, almost as good as a dipole. The gain is 1.48 dB. It's only a half a dB worse than a dipole. It all looks pretty good until I get down here where it says the required added capacitance needed to resonate the loop on 30 megahertz is, what is it? 11.25 picofarads. The minimum capacitance I have here is 15. So it's not going to tune it. Yes, in theory it'll work because the loop is still less than a quarter wave in circumference. But the limitation I got here is the minimum capacitance is too high. The loop won't reach 30 megahertz. Let's say I really got silly and ignored that, and I said, let's try to make the frequency 36 megahertz. Uh-oh. What happened? Notice everything went blank. It's too big. I'm trapping the error because I'm telling you that a 34.5-inch diameter loop, if you try to operate it at 36 megahertz, is beyond my requirement for small loop. It's longer than quarter wave. Can't get there from here. So I trapped the error. All right, so that's not going to work. Looks like the highest ham frequency I can cover is 25 megahertz. And if you look at my capacitor Q at 25 megahertz, way over here, it looks like it's about 1,250, maybe 1,100. I'll put that number in. and everything else is the same. Okay, 100 watts, same dimensions. Okay, so here I've got, not quite 0 dB gain, 59% efficient. It looks like it's as good as a isotrope, within a half an S unit or so of a dipole. And the bandwidth is reasonably good, 145 kilohertz. As people that operate 12 meters know, that band only goes from 24.8 to 25, 200 kilohertz. It'll cover the whole darn band almost, so you won't have to retune it up there. If we examine the behavior, let's say on 21 megahertz, 15 meters, let's see, the Q on 15 meters is about 2200 or so. We'll put that number in for the capacitor. And it looks like it's got 0 dB gain, as good as an isotrope. It's a Q of about 300, a 71 kilohertz bandwidth. Obviously, it won't cover the whole band, but reasonable. The performance is good, the gain is good, it'll tune, and it's pretty comfortable. The capacitor only has 2800 volts across it, and if we designed it for 14, it was already designed for 3100, so it looks like that'll hold together. And so it looks like the design holds together from pretty much 14 megahertz all the way to up to at least 25 megahertz. I didn't match it yet, because right now the radiation resistance is about 0.2 of an ohm, almost 0.3 of an ohm, with a loss resistance of about 0.19 ohms. Obviously nowhere near 50. So we need some more work to be done. And this computer program, in fact, any of the analysis programs that I have, like the EasyNet, don't have the ability to work with these kinds of small numbers. So you go on your own. The only way to achieve a match then would be to kind of plow through it yourself. Now there's two approaches to the match. N2PPI, Mike chose the high-side C coupling loop match, which is fine. I happen to choose the gamma match, which is fine too. Either one is equivalent. There's no particular benefit of using one or the other. Which is easier to build? I don't know. I don't think there's any benefit either way. Just a matter of your choice. All right, now we got to match it. Well, the first thing I think I'd like to do is to try to come up with an equivalent, parallel equivalent resistance, because before we calculated everything in series. The inductive reactance is in series with a series resistance. The way I'm going to design the match is the match is in shunt. It's in parallel with some point on the antenna, so we got to convert to parallel. The way you convert to parallel is by calculating what I call RP. It's the total series resistance divided by the total series inductance squared divided by the series resistance. Okay? And of course, these are numbers that you calculated prior. At 14 megahertz, now this is based on spreadsheet. You can read this off for yourself if you want, but at 14 megahertz, RP is 49K. 18 megahertz RP is 41.7K, and at 25 megahertz RP is 27.9K. Kiloohms. That's why the voltage is so high, obviously. Now, what does that mean? Can a single matching circuit, since we got 3 different values of resistors, can a single matching circuit be used to match all 3 values? That's the problem. Uh-oh, the police. Oh, Phil, thank you. Thank you very much. Appreciate it. Thank you. Thank you. Oh, my pleasure. Thank you. Thank you. Thank you very much, Phil. Thanks. Appreciate it. Oh, so again, how are we doing on time? Can a single matching circuit be used on all bands? Obviously, I don't want to have to, every time you change frequency, figure out a way to come up with a new tap. That would be, if nothing else, inconvenient. So let's see if it's going to work. If I tried to design a single matching circuit for, let's say, the middle, which is about 18 megahertz, would that same matching circuit hold together with the other bands? In other words, if I find the location for the best tap on one frequency in the middle, like right there, would that work also for the low end and the high end? Well, let's take a look. The VSWR that I would get on 14 megahertz if I designed for 18 would be the value of resistance you get for 14 divided by the resistance you get for 18, 1.17. If I can come up with close to a perfect match on 18, the match will be better than 1.2 on 14 megahertz. Well, that sounds okay. But what happens on 25? Well, the VSWR that I could expect on 25 is the resistance I get at 18 divided by the resistance I get at 25, 41.7K divided by 28K, 1.49. Well, that's okay. So it looks like it'll hold together. In other words, design it for a match on 18 megahertz as best as you can, locate the tap, and that's empirical, by the way, that's experimentation. There's no calculation, that easy calculation that I know of that's going to do that. and then it looks like it holds together on the band edges. Of course, the question comes up now is, what kind of match do you want? High side C, Mike's approach, or small coupling loop, or a gamma match? Either one works. I chose the gamma match for this design. Now, how does a gamma match work? In case anybody isn't aware of it. Here's my loop. The loop on one end is grounded. It's connected directly to ground AC-wise. In other words, there's bypass capacitors that connect that loop to earth. At the very end, where the capacitor tuning circuit is, it's about 40K. You got a short on one side, 40K on the other side. Well, somewhere between a short and 40K is 50 ohms. You find that point. That's where the gamma match gets attached, right there. Okay? Simple. Somewhere between a short and RP is where the match gets connected. So you realize it like this. You have your series circuit consisting of an inductive reactance, a capacitor, antenna resistance, capacitor resistance, radiation resistance, transformed to parallel. That gives you RP. Okay, we can do that transformation. I gave you that calculation before. The spreadsheet calculates it. Then design the gamma match. The gamma match is analogous to a tap transformer. Someplace in this inductor, this is like an auto transformer. You find the tap that gives you the value that you want at 50 ohms, and you connect your gamma rod. Now, the gamma rod is going to have its own inductance, and it's going to have its own capacitance. The capacitance, of course, is this excess stub over here, if you can see it, and the actual length of the gamma rod itself is the gamma inductance. It's about 20 nanohenries per inch. Now, you can calculate it, or you can empirically determine it. Makes no difference. It gives you the match that you want. Make sure you do it in the center, though, at 18. And this is what it looks like. You can come up and take a look for yourself. But starting with the antenna on this side, there's the tap. Now, why do I use capacitors? Anybody? Why not just connect it directly? There's DC on here. I got to tune the motor. Otherwise, there'd be a short. The motor, 12 volts, would be connected shorted to ground, so I got to isolate it through some coupling capacitors. That's what the gamma match looks like. Simple enough. Oh, in case anybody wants to know what that is, that's that same rod they hold the, what do you call it, the pipes up. The plumbers use it to hold the pipes on your ceiling. It's copper. Cheap enough. The tuning unit itself, and you can come up and look at it, is the capacitor. The heavy leads, I double up on the wires. The loop is split over here. The capacitor is in series with the loop. There's an insulated Rexolite plastic bushing over here, which insulates the hobby motor from the capacitor. This is an RF choke to keep the RF out of the motor. The actual center conductor itself is a choke over here, which runs up inside this PVC tube, inside the housing, another RF choke, which prevents RF again from getting in the motor and only allows DC to get to the motor, and the shaft prevents the RF from getting into the motor also. Typical electronic remote tuning unit, no big deal there. The hobby motor is about $3. Very, very cheap. You can see the Chinese writing, well, that's why. But you need a control box to tune it. Here's the control box. I have a schematic of it. Now, in the control box itself, there's two RF chokes. Again, the RF chokes prevent the RF from getting into the rest of the electronics. This, which is hard to see, is a 3-terminal regulator. This connection over here brings in somewhere between 12.8 and 15 volts. The 3-terminal regulator regulates it down to 10. I even further drop it down through a series resistor because the motor was rotating a little bit too fast. It was hard to tune. So after I make 10 volts, I drop it to about 8 volts through this dropping resistor. 8 volts is then allowed to tune the motor. This is a reversing switch, center off, so it either tunes right or left. So the motor can go both ways in case you went too far. And here's a schematic of the unit. 3-terminal regulator, protection diodes, reversing switch. Now, there's 3 capacitors in series. This side is where the exciter connects. This is where your radio connects to, and this is where the antenna. I want to keep DC out of the radio, obviously. These 2 capacitors, C12 and C11, provide a little bit of tuning. It turns out because I have about that much of lead length inside the tuning unit, there was a small amount of reactance that I tuned out, and I simply made a low-pass filter, which guarantees that the match between J2 and J3 is much, much better than 105. And then, of course, there's DC on the shield side of the antenna, So I can't connect that directly to ground. Instead, I connect it via an AC ground via these three bypass capacitors here. Okay, and this is a double pole, double throw, momentary switch, center off, so I can tune in both directions. L1 and L2 are the chokes, RF chokes, that you can see in here, the two toroids covered with gray wire. So that's a simple enough design. Okay, now how did it work? I built it. Well, first of all, let's talk about the VSWR as measured on my MFJ analyzer. 14 megahertz, the match is 1.2. 18 was 1.1. 21 was 1.25. 25 was 1.4. Pretty much in agreement with my calculations. And of course, I couldn't tune 28, again, because I didn't have enough minimum capacitance in the capacitor. But up to 25 megahertz, it met the design specs. How long does it take to tune? Well, about 8 seconds, because the motor's running very, very slowly. The qualitative gain. Now, this was a very qualitative measurement. There was a day when there was pretty good propagation to Europe. There was a good path, which is a one-hot path. I was using Italy at the time. And I have my dipole as a comparison antenna, which is up at 43 feet. This antenna was mounted in this plane, 12 feet up. So we're comparing this at 12 feet to a dipole that was up at 43 feet. Switching back and forth very quickly after a number of trials, the gain at 14 and 18 megahertz was about a half an S unit from the dipole. Pretty respectable. And at 21 and 25, I didn't see any difference at all. I mean, nothing that I could see. And I did, again, I was there 10 minutes trying to switch back and forth very, very quickly. And it seemed like that there was no difference that I could discern on the two high ends. And the antenna was at that time oriented in the vertical plane like this, which was then pointed towards Europe. By the way, this antenna in this plane radiates better in the direction of the loop, and there's a null at right angles to the loop, okay? Power capability. Well, I took my transmitter, set it for 100 watts, keyed down for 30 seconds. Might as well see if it's going to survive. After 30 seconds was up, I quickly went to the antenna. The capacitor itself was slightly warm to the touch. I mean, above room temperature warm, not hot. But the antenna itself was ice cold. So it looked like there was no particular issue with power losses at all. I couldn't push it any higher than that. Somebody might say, we'll go to 200. Remember, there's a voltage breakdown problem. Just because you don't have a power problem doesn't mean you possibly could not have a voltage breakdown problem. Hell no. You guys are wise guys. There's 3,000 volts on that capacitor. The 2-to-1 VSWR bandwidth before you have to retune. And this agrees pretty closely with the theory, as it turns out. At 14 megahertz, it was just under 20 kilohertz. 18 megahertz, about 30. 21 megahertz, about 70. And at 25 megahertz, 12 meters, it was about 130 megahertz. Pretty respectable. Now, how much did the darn thing cost? Okay. Well, I itemized the list. The box for the tuning unit, the box for the antenna, there's the eBay specials, the hobby motor, the variable capacitor, connectors, the 3 pieces of ferrite, disc capacitors, the regulator, the diodes, the hula hoop. The hula hoop was $5. It was really $2.39. But I carried it as $5. Anyway, the whole thing came out to be $74.50. And I really bought everything. I really took nothing out of the junk box. I tried to be honest as I could and come up with an itemized list as accurately as I could possibly get. So it met the design goal for $100, thank goodness. So in summary, am I going to end early? I never did before. The design goal was to achieve and construct a high-performance, low-cost antenna, and I think it pretty much did that. The VSWR definitely was less than 1.5 to 1 on all the bands, using the gamma match. The gain, based on measurement, qualitative, was about a half an S unit from a full-size dipole. And it looks like that this power capability certainly was in accordance with a barefoot receiver in the 100-watt class. The bill of materials met the budget of less than $100. Now, the thing I do like, though, is that the antenna really nicely offers 2 options. You can mount it in the vertical plane. Now, what happens when you put the antenna in this plane? 2 things are good. You can mount it directly on ground. It's pretty much a ground-independent antenna because the whole loop itself is part of the antenna structure. It doesn't need a counterpoint. But the better feature is that when you mount the antenna this way, it radiates at all radiation angles, from the horizon to overhead. So not only do you have an NVIS structure if you want it, you also have a DX capable antenna. So somebody might say, well, why don't you just do that? Well, it's got one disadvantage. It's directional. It's bidirectional. So it has to be tuned in the direction that you want. Off to the sides at 90 degrees, it's got a a deep null. It's gone, 40 dB or more. It's got a very deep null. So it's got one undesirable property. You can put it on a rotor, but the nice thing is on ground. So his antenna you couldn't put on a rotor because he has to manually tune it. This one you can because of the motor feature. But you're quite right, you could put it on a rotor. In this plane, which is the way I got it now, it radiates pretty much exactly like a dipole, except it's omnidirectional. An omnidirectional turnstile dipole. Now, the problem with that is it radiates like a dipole, which means in order for it to work as a DX antenna, it's got to be up a quarter wave or half a wave, approximately, or higher. Or else, you do have an NVIS dipole. So if you wanted an omnidirectional antenna, this is the plane to mount it in, but up high. If you want an all-angle antenna, you mount it this way, and you can mount it anywhere you want. Okay? That was a nice feature, as it turns out. It's a nice, attractive, portable antenna. Mike actually puts this in the trunk of his car. He can break this down in about 3 minutes. Mine, not so easy. I got to remove some screws. But his comes right apart. Now, we used to have these excursions to Wantua Park in the summertime. And we bring these things down there. You made a couple of contacts to Europe, and so did I. 20-watt transceiver, which is right here. These antennas you put up in a few minutes. And on good condition days, Europe is no problem at all. Q5 signals Europe. First time I brought the antenna down to our club, Nassau Amateur Radio Club, for some reason people were working a pile-up on a Puerto Rican station. So I figured, what the heck, I tried to join in. And sure enough, second call, I got him. That was with a 100-watt transceiver. Not a big deal, but, kind of feel good when you have an antenna that's you can stick in your pocket and you can work a pile-up. So that was good. So it is kind of attractive. Well, that's the end of my presentation. Anybody have any questions? Sir. As far as efficiency is concerned, probably not. I think either one would give you about the same performance. The purpose of this antenna, I guess there were two. My secondary goal was, to try to compete with Buddy Pole, but the primary goal was, can this be done at all using cheap components? It was kind of I guess an investigative effort on my part to see if it could be done. Now, MFJ and a few other people sell these antennas for $400, for God's sakes. And after you look at what I did and what Mike did, you say, well, what in the freaking hell does it cost so much money for? It makes no sense. Yeah, Mike, go ahead.
This is an Alex. Really look at it.
No, he's going to yell at you.
Now, yeah, I got a big mouth.
You want to take yeah, hey, we got a radio connected to his. You'll listen to room noise. Listen to what happens when you get to resonance. How about that? Mine does not have that feature. He decided he wanted a tuning indicator.
The reason why I wanted to do that was because I'm working out here, and I wanted to tune for best visual. I found out the best way I could tune the best visual, instead of me trying to fiddle around with this, all I would have to do is get close to noise like I just did.
What he's doing is he's tuning for maximum current in the loop. Tune. What band were you on?
I was on 15 meters. This loop here works 15 meters to 40, based on the capacitor I have.
I'm sorry? Oh, all right.
Oh, I'm sorry. I didn't even how you doing, everybody? So basically, like I said, this antenna here is represents 15 to 40 meters, and that's based on the variable capacitor in here. And going back on what I said before was, this is a field strength meter, which I mounted on top here. I built a little circuit for an antenna so it picks it up. And basically what that's for is because I use it out in the field, in the parks and everything. It breaks down real easy, and it goes into a bag like this. It's really simple. And I'm able to sit here on my KX3 right next to me and tune right Viswar 1-to-1 with no problem. All I'd have to do is listen to noise and basically look at the field strength meter. And when I got full field strength, I know I'm at 1-to-1. I check it on here, and it's 1-to-1. So it's a really nice feature to add to it. You know, I'm full of bells and whistles. I like to play around this. I build things. They'll tell you. I'm constantly bringing things down to the club to build and everything. And here's another thing that I liked about this is that I was playing around with wire. I was playing around with coax. You know, trying to build this loop. And by chance, I said, oh, I had this laying around. I had this refrigerant tubing laying around. So this would be good. Let me try it. It's 3/8. I looked at some of the calculators that had a 3/8 calculator on there. Yeah, that's fine. And basically what happened was I said, look at these SO239s I had laying around. I said, you know what? I said, hot stuff. It actually fits directly in here. It doesn't matter. You can do it on 0.375. So basically, I put this in here, and I took one of those little mini torches, the ones that the soldering irons that they have, the torches that they have with you take the soldering iron part off, and you got a little torch. You light it. It's got a little mini torch. Took some solder to it, brazed it, and sure as heck, I mounted this. So basically, the hot side is on the shield side of this. I mounted two SO239s inside here, and that's basically for support. So the inner conductor isn't even connected on the SO230 on the PL259s here, and the SO239s. It's the shielding. So all you're getting is that, and that's basically only was for support, and it worked out quite well. I've made many contacts into Europe, South America. I've even worked Africa with this thing at a park. 10 watts, 12 watts with the QRP and this battery right here, and it's really cool antenna actually. What I like about it, believe it or not, a lot of people, complain with the high Q, constantly always have to tune things and everything, but I'll tell you what, you don't hear that side noise. You don't hear that side, you really don't hear any of that garbage that's on the side frequency. So if you really want to pull somebody out, you can really have a good opportunity to pulling people out of the mess.
This is a magnetic loop antenna, not a shielded magnetic loop. Some people are familiar with the receiving loops. This is not that kind of structure. This is a magnetic loop, but it does work on a magnetic field principle rather than an electrostatic and magnetic field principle. Therefore, it responds more readily to a magnetic field. Most types of man-made noise, like the 60 hertz line noise that you have power line, and also terrestrial lightning, static crashes, those are impulse electric disturbances, which means this would have some kind of discrimination against the electrical noises. So if you were in a noisy environment where you had a lot of man-made noise for whatever reason, this thing would offer, and I measured about 2 S units improvement on receive. So not only do you get approximately the same efficiency for transmit, but you also get 1 to 2 S unit improvement on receive most of the time for most types of disturbances. And that's a big plus if you're trying to pull a weak guy out of something.
Yeah,
okay?
I've actually demonstrated this with a dipole antenna. I had a dipole and this put side by side, and what I noticed is when I had something really strong on the side of me, I was hearing it. It was hashing over on, I was hashing over with the dipole. When I got on this because of the IQ, once I was on frequency, that was gone. So it makes it it's so good and bad. If you like the retuning bit, yeah, nobody wants to retune every 2 minutes. But in the same respect, you're getting good quality signals coming through on frequency. So.
Anybody else? Sure. That was volts peak. I'm using peak envelope power. That was peak. No, I'm using 100 watt peak envelope power, so that already includes it. The 100 watts is peak. Peak. No, I'm using peak envelope power. I purposely use peak PEP. When a CW signal or a sideband signal are rated in peak, it is a peak. Yes, sir. Yes. There's no 40% yet. No. No, you do not. Yes. You'll have to recalculate it. The equation that I use to calculate inductive reactance is based on Gauss's law, pure circle. You can use other topologies, but then you're on your own. You got to design. You got to come up with your own equation. Not that it's so terribly difficult, but no. Ellipse or something. Yeah. Oh, a 5% difference either way. No. That's taken up in tuning. No. Don't forget, we're tuning it. So 5% either way doesn't matter. We're not putting a fixed value of tuning C in there.
But I'll tell you what, they are very directional. Because I've worked with many guys, and moving this antenna like this, I mean, they'll tell you when I'm in the US.
Oh yeah, absolutely. Or down.
It's really, or down. Yeah, it's great. They really know a lot of,
There was a question of yes. Well, I'm in a weatherproof box too, but if water does get in there, obviously it will affect the arc over voltage. Yeah, I would say this is a high maintenance antenna. Every 6 months, you probably want to get out there and dry it. I would say, or come up with some way to get the darn water out. Yeah. To me, well, there's weep holes in my design, so if water gets in, I let it out the bottom. Okay, but it's going to get in. Now, the only way you're going to prevent water from not getting into something is make a hermetic seal, and this is not a hermetic seal. Oh, yeah.
I'm a real short big guy. I gotta go outside. I love being outdoors in any situation. I like being outdoors and playing around in the park. And I've side by side with this thing will match up with the buddy pole, 100%. The signal reports are pretty much dead on. So it depends what you like. I like both. I mean, I'm not putting the buddy pole down because I like the buddy pole. I own tuned them. So a lot of times what I'll do is I'll put this up for experimentation. I'll put this up and I'll face it one way and I'll have the buddy pole in a vertical and I'll put the other one in a dipole and work them in different directions. So it's a lot of fun. Did we? All right. Well, thank you very much.
No, thank you all. We appreciate it. Thanks for hanging in at 2:30. Appreciate that. Very good. Thank you all. I do remember you, but I was looking at you. I'm saying, where the heck do I know that guy from? Yes, I do remember you.
Working with Steve Sabay, you know him?
Yes, sure. Where you guys?